All right, with chapter 2, it's about bonding, right? So we start the chapter off with the ionic bonding. So here we have red cations and blue anions. And with A, they want to know which combination of these ions produces one-to-one ratios of cations to anions. So as we know, if we're going to form an ionic compound, the charges, the sum of the charges on the cations and the anions have to cancel, right? No charge in the compound. So the way you would do this, you would line up the A cation with the Y anion, right? A plus 2 charge and minus 2 charge, and they cancel each other. That'd be a 1-to-1 ratio in the crystal, something like calcium oxide. If we wanted a 1-to-1 ratio with the plus 1 cation, we need a minus 1 anion, and something like sodium chloride and, actually, it wouldn't be such a big cation, I don't know, cesium chloride. And we'd have a 1-to-1 ratio of the plus 1 cation to the negative 1 anion. All right. B, among the combinations of part A, which leads to an ionic compound having the largest lattice energy? All right, lattice energy is how much energy is released when these ions come together. And it's determined by charge. All right, so Q1 times Q2. So what this equates to is if you have a large charge on the cation and a large charge on the anion, you're going to have a large lattice energy. And if you have small ions, right, a small d value, right, small distance between the ions, you're going to have a large lattice energy. So what we want for large lattice energies are small, highly charged cations. Well, it's kind of like mixing apples and oranges here. It would have been nicer if they had, a smaller negative 2 anion than the negative 1 cation. But nonetheless, the fact that you've got a plus 2 charge and a negative 2 charge is going to give you a greater lattice energy with an AY compound than with a BX compound. So the BX compound would have a lower lattice energy because of the smaller charge, right? It has a plus 1 charge and a negative 1 charge, and looking at the sizes here, they're about the same as the combination is about the same as the AY. So this is about charge with these 1-to-1 ratios. All right, we have an incomplete Lewis structure for nitrous acid and nitrite ion. Complete the Lewis dot structure by adding electron pairs as needed. And, let's do that first, right? So we count up the electrons, and the rule is the more electronegative element gets the electrons first, the less electronegative element gets it second. So the first one would be the Lewis dot structure for nitrous acid, and the second one would be the electron configuration for nitrite. B, is the formal charge on the N the same or different in the two species? Well, formal charge, right, so no, they have the same formal charge. They're not different. Formal charge is defined as the valence number minus the electron count. Electron count is the electrons owned by the atoms, right? So that's 1 and plus 1/2 the bonded pairs. So for every bond, you count it as 1, and for every dot, you count it as, for every 2 dots, you count it as 2. So I have a valence of 5 for both of the nitrogens. Nitrogen's got 5 outer electrons, so in group 5A. The electron count for nitrogen number 1 is 1, 2, 3, 4, 5, and the electron count for the second nitrogen is 1, 2, 3, 4, 5. So 5 minus 5, there is no formal charge on either of these nitrogens. There is a formal charge, however, on the oxygen in nitrite. All right, electron count of 7. All right, so 1, 2, 3, 4, 5, 6 unpaired electrons plus 1/2 the bonded pairs gives me 7. Valence of 6. 7 minus 6, I got a minus 1 formal charge on that oxygen. All right, C. Would either of these, nitrous acid or nitrite be expected to exhibit resonance? Right, so we could put the double bond on the second oxygen of nitrite, or we could put it on the first. Either way, I have the same amount of formal charge. So the fact of the matter is we don't have a true double bond between either of these oxygens. It's a hybrid. It's a mixing of a delocalization of the electron pair over all three atoms. So we put the double-headed arrow to indicate that both Lewis dot structures are needed to show that there's delocalization with that extra bonded pair of electron. All right, it's can't be localized on either of the oxygens. So when you do this, you're right. You blend these double bonds with single bonds, as we know from the lecture. The more electrons you share between the atoms, the shorter the bond length. All right. So with a single bond, you have a longer bond. With a double bond, you have a shorter bond. Well, with resonance, it's not really a double bond. It's not really a single bond, right? So the single bond in the resonance structure is a little shorter than it should be, and the double bond's a little longer than it should be. So it's a mixing. So the double bond in nitrite would be a little longer than the double bond in nitrous acid, which is a pure double bond. You wouldn't put the double bond between the oxygen and the N on the first oxygen with nitrous acid because, well, bunch of reasons, right? Oxygen can only bond to two things. Can't have a double bond there. So with resonance, you get a hybrid, right? You don't really have a double bond. You don't really have a single bond. You have a mixing of a single bond and a double bond. All right, we have a partial Lewis dot structure, right? We have 4 carbons, double bond, single bond, triple bond. They want us to determine where the hydrogen atoms in the molecule are going to go. So this is a hydrocarbon. You have to have hydrogens attached to this. Is incomplete. So carbon can bond 4 times. So if you've got a double bond, you can put 2 more hydrogens on carbon number 1. You can put 1 more carbon on carbon number 2. You can't put any more bonds on hydrogen number 3, and hydrogen number 4 could take 1 more bond. So this is the molecule that you'd be left with. Okay. So they have the bonds numbered, bond number 1, bond number 2, bond number 3. They want you to rank the carbon-carbon bonds in order of increasing bond length. So as we said before, single bonds are longer than double bonds are longer than triple bonds. So in terms of bond order, bond number 3 would be the shortest and bond number 2 would be the longest. C, rank the carbon-carbon bonds in order of increasing enthalpy. If you're going to break a bond, you got to put energy in. So which of these bonds is hardest to break? Well, the more electrons you share between the atoms, the more strongly bonded they are. So a triple bond is stronger than a double bond. A double bond is stronger than a single bond. So the triple bond would be the hardest to break, and the single bond, bond number 2, would be the easiest to break. So that's how bond energies and bond lengths relate to each other. What are valence electrons? Valence electrons are outer electrons, as opposed to core electrons, which are on the inside, shielding the outer electrons from feeling the nucleus. B, how many valence electrons does the nitrogen atom possess? Well, nitrogen's in group 5A, so it has 5 valence electrons. A helium core. The 2s has 2 electrons, and the 2p has 3 electrons. C, an atom has the electron configuration 1s2, 2s2, 2p6. All right, so that's a neon core, and we're adding on to that. 3s2, 3p2. So how many valence electrons does it have? Well, it has 4 valence electrons, right? These are the core electrons, and we have 4 outer electrons in the 3rd energy level. Nice review from chapter 6. 26. Explain the following trends in lattice energy. All right, so lattice energy is equal to the charge of the cation times the charge of the anion divided by the distance between them. So what this equates to is large charge, small ions give you a large lattice energy. So if we look at the periodic table and compare sodium, rubidium, and cesium, right, all group 1A metals, we see that sodium is the smallest, cesium is the biggest, so you'll have the lowest ionization or lattice energy with cesium as opposed to sodium, right, a bigger ion. And if we compare chloride to bromide, right, they're both halogens, Chloride is a smaller anion than bromide. So sodium chloride is has the largest lattice energy because of size, right? It's the smallest cation and anion, and with cesium bromide, you'd have the largest cation and with the largest anion. So that's the rationale as to why larger lattice energy with sodium chloride as opposed to cesium bromide. Looking at B, lattice energy compared to barium oxide versus potassium fluoride. Now, potassium is going to be a smaller ion than barium, but the big difference is that barium has got a +2 charge. And if I'm comparing oxide to fluoride, oxide is going to be a little bit bigger, but it's going to have a -2 charge. So if they're saying that barium oxide has a larger lattice energy, it's because of charge. A -2 charge and a +2 charge is going to be a greater attraction than a +1 charge and a -1 charge with potassium and fluoride. So it's not about distance between them, right? The size, it's more about the charge on this one. Strontium oxide is bigger than strontium chloride. All right, so if we're looking at C, I can see right off, right? Oxide has got that -2 charge, and chloride has the -1 charge, right? So you've got oxide with the greater charge, and it's smaller, right? It's further to the left of the period and higher up in a group. So you got both things working for you with oxide, higher charge and smaller size. All right, 28. List the individual steps used in constructing the Born-Haber cycle for the formation of barium iodide from the elements. Which of the steps would you expect to be exothermic? All right, the Born-Haber cycle is basically adding up energy inputs and energy releases to go from reactants to products. And in the case of an ionic compound, you have to, if your energy inputs are way greater than the energy releases you're going to get, you're not going to get an ionic compound. You get some sort of molecule, all right, some sort of covalent compound. All right, so you're just adding up energies here. If I'm going to react barium and iodine to make barium iodide, the first thing I have to do is get barium out of the solid phase and into the gas phase. That's an energy input, right? That's an endothermic process. I'd have to put energy in to do that. Now it's ready to have electrons knocked off of it, right, to make barium +2 ion. So knocking the first electron off costs you energy. Knocking the second electron off costs you energy. Now notice I try to do this with the drawing here. The longer the arrow, the more energy I had to put in. So putting barium in the gas phase costs you a certain amount of energy, but knocking electrons off costs you way more energy, right? So first ionization energy is always less than the second. And at this point, I've put in energy, I've put in energy, I've put in energy, right? So these are all endothermic steps. If I'm going to get iodine prepped so that it can take those electrons I knocked off of barium, I first have to break the single iodine-iodine bond to get iodine atom by itself. All right, again, the dotted part is just to bring you up to the top here, right? It's not that big an energy to, bond association energy to break the iodine-iodine single bond. So these all have been endothermic steps so far, right? But now I've got iodine atom and I've got electrons knocked off. So when the iodine atoms take electrons, become 2 moles of iodide, that's going to be a releasing process. Whereas steps 2 and 3 were ionization energy, represented ionization energy. This step, making iodide, is electron affinity, or an energy releasing process. So at this point now I've got the iodide ion and the barium ion. The big release in energy in the formation of an ionic compound is the release you get when these ions in the gas phase go to the solid phase, form the crystal. And that's lattice energy. So really, it's all about the lattice energy. If you have a large enough lattice energy, then you'll get a big enough energy release to justify an ionic compound. If you don't have a large enough lattice energy, you're not going to get an ionic compound. So this is the Born-Haber cycle. Energy inputs, and the energy releases.